back.
Okay, shall we start? Okay, we're very happy to have Robert Lipshitz from University of Oregon, also from upstairs in the MSI, to give us a talk about the Floer homology of three manifolds with boundaries.
Great. Thank you very much for inviting me. It's really nice to have a chance to talk to you. My understanding is this is in some sense a 2-hour seminar.
Yeah.
But I was going to give a 1-hour talk. We'll see where we get, and then I'll do what you want after that. So it can be over or it can continue. And please ask questions. The talk is, I've written it to be fit, just start right at the beginning and be very sort of down to earth and sort of introductory. If you're bored, you can tell me to speed up. So it's possible to go faster. But I don't assume, I assume you know what a manifold is, but I'm not assuming anything else. A manifold would be fine. So the plan is I want to tell you maybe the first half hour or so about Heegaard Floer homology itself, what it is, and a little bit about the definition, sort of a hint of what the definition is, not a complete definition. I'm going to give you a couple of examples of things that it's used for. And then the second half, I'll talk about this extension to manifold. So Heegaard Floer homology, this is due to Ozsváth-Szabó from roughly 2000. Well, continuing, this is due to me and Ozsváth and Thurston from 2008. Well, in both cases, developments continue, so it's not all as old as it sounds. So Heegaard Floer. So this is a analog of Seiberg-Witten theory, Seiberg-Witten invariant, or Floer homology, Seiberg-Witten Floer homology, defined via holomorphic curves. So what does it do? It takes a closed free manifold, and there are a couple of variants. I'll say what they correspond to in a couple of minutes, but it gives you a chain complex denoted CF hat of Y over Z. And there's another version, CF minus of Y. Well, there are a few others. CF minus, CF plus. There are others over Z bracket 0. So I'm going to polynomial ring. And okay, if you have a chain complex, then you also have its homology. So it has homology. Homology. HF hat of Y. Or HF minus of Y. Right. This one is sort of the fundamental object. So this is the one to remember. In the sense that if I take, if I want to get CF hat back, CF hat is just CF minus mod the action of U. So mod U CF minus. So you just said that is CF minus. And then CF plus is you just take, you invert U, so CF minus of U, tensor Z adjoint U, U inverse, and you kill off CF minus of Y inside that. So in CF plus, so in CF minus, let's say U, I'm going to perversely make it go down. So here's, so I've drawn a picture of, this is C brackets U. C brackets U, I've got a generator 1, U squared, and so on. then so that's what CF minus of y sort of looks like. CF plus looks like you take if Taurus in both directions. Right? Here's maybe one, and then you kill off all this stuff, so everything becomes unitorsional. So the thing at the bottom you multiply by u, you get 0. The thing at the bottom you multiply u twice, you get 0. So it's fine. Okay. So I said these are isomorphic to Seiberg-Witten or monocle Floer homology. If you've seen that before. So if you haven't seen that before, the next just ignore the next 2 minutes of what I'm going to say. But the notation is HF minus is what they denote HM from. And HF hat is so this is somehow this is like an S1 equivariant homology or cohomology. And HF hat is the non S1 equivariant which doesn't show up as often, so it's sort of not a lead combination.
In which sense S1 equivariant? Maybe.
Yeah.
Okay.
So I say another word about that.
So let's see. So Seiberg-Witten Floer. So you're studying the Seiberg-Witten theory on Y3 times R.
Yeah. So I will try. So here there's a gauge group so the gauge group is like maps from Y to U1. And inside that there's a base gauge group, so this contains a base gauge group G0, which is like maps from Y to U1. Set of G in G, such that maybe G of some point, I don't know, some point P is equal to for some, so you pick some point P and Y and require that. And the point is that this thing acts freely. So G naught acts freely, but G doesn't if you have a reducible connection. So if you have a connection with a spin of 0, sorry, a reducible solution so with a spin of 0. And so what people do is they look at roughly they consider some space of solutions. My notation won't be standard, but like X of the Seiberg-Witten equation. And then they look at X mod G0 because the action there was free. So that's sort of a safe quotient to take. And then look at that cross, what's the like S infinity or E S1. And then mod an additional S1. And this is the equivariant, what I mean by the equivariant, S1 equivariant homology. So here, S infinity has an action by U. This is the unit sphere in C infinity. So this is an action, a free action by U1. And so this is a way of making the action by the remaining S1, remaining U1 free. So I should have been U1. And then you take the quotient. So there's some extra mess at the end, and then this comes with a map to CP infinity, just by forgetting the first factor. CP infinity is S infinity mod U1. And so that this U that keeps showing up is a generator of the cohomology of CP infinity. Great. More questions or follow-on questions?
So you said G0 acts freely?
Acts freely on the space of potential Seiberg-Witten, of possible Seiberg-Witten solutions. Yeah, that's right. So that's right. So the issue is that you, so a Seiberg-Witten solution is a section of some spinor bundle, a spinor, and also a connection on some associated U1 bundle. And if you look at the ones, so this whole thing acts freely almost everywhere. The problem is when the spinor is 0, it doesn't quite act freely, but this one still acts freely.
And you think of this as, well, I guess you'll tell us in a moment, right?
Yeah, that's right. So I wasn't going to motivate. I'm happy. I wasn't going to say that, but I'm happy to say that after I say what the definition is. Yeah, I mean, at least the philosophy of why it's supposed to be, why it's true.
Oh, actually, I have a question. Is there an extension of this? Has somebody worked out the extension of this or not?
What a good question. That's 3 sentences later in my notes. Let me say the other 2 things first, but then yeah, I'll say that. Sorry. So this for knots, I'll say in a few minutes.
Yeah,
the correspondence is not proved for knots. This side is sort of messy for knots, but there are a few different approaches and in different states of completeness. That's a good question. There are a bunch of young people who have been students of Kronenheimer and Rufka who've been doing this sort of thing, but I won't get the names right. Maybe there's some mathematicians in the audience in the back who might be able to help. Do you know who's working on monopole Floer homology for knots? Say it louder. I'm still not, sorry. One. Same word. Okay, sorry, I'm doing great here. Okay, good. So HM for knots. Thanks, Leah. Sorry? That's probably true. Yeah, I mean, that's right. So that's right. There are a bunch of like sutured monopole Floer or sutured instant tunnels. So that's another sort of keyword. That's right. There's a trick. I mean, there's an earlier paper of Kronenheimer and Rufka. So, sorry, I don't know quite as little as I sound like, but there's an earlier paper of Kronenheimer. Oh, I'm being recorded. That's awesome. I'm glad to have totally screwed up the giving people credit. There's a earlier paper of Kronenheimer and Rufka that gives also a version of this for knots. That's sort of a version of the hat version, not the minus. By some trickery, you delete a neighborhood of the knot and you glue something in, and there's some trickery that gives you yeah. More questions? Yeah, I should have. Mathematicians were here at the beginning where I told you you're going to be bored and irritated, probably. Okay, fine. These things decompose along spin C structures. That's not going to. So I think probably for physicists that doesn't bother you. Mathematicians who are not in the field tend to tune out as soon as you say spin C structure. But these decompose along spin C structures. So like CF minus, say, is a direct sum over spin C structures on Y of CF minus of YS, which is useful. I mean, turns out to be important technically in some places and useful if you want to do things with it, but I'm just going to suppress. Bit too much physics there. Okay. And there's so where's the Seiberg-Witten invariant? Oh, sorry. So something before that. So it's some sort of TQFT. So given a four-dimensional smooth for the cobordism W from Y1 to Y2, you get an induced map, call it FW hat from CF hat of Y1 to CF hat of Y2, etc. And again, these decompose along spin C structures. And composing cobordisms corresponds to composing maps. Gives you composing maps. Okay, and it is defined for Z coefficients. That's a good question. Yes, and the maps work with Z coefficients, although the functorial, I mean, this statement is only known up to sine with Z coefficients. There's supposed to be some homology orientation, something or other, but nobody's actually written that down. So this is sort of true up to sine. Yes. And where's the Seiberg-Witten invariant? So Seiberg-Witten invariant of some closed x. So you look at x minus 2 four-balls. That's a cobordism from S3 to S3. You think I'm going to say you look at the map associated with that cobordism, but it's a little bit, that map is usually 0, so it's a little bit more complicated than that. So, so I need to assume that B2 plus of x is at least 2. So decompose this x minus B4 minus 2 balls as a composition of 2 cobordisms, W1, W2. So maybe I should draw it. So like here I've got, here's S3, and here's some Y in between. Here's S3 again, here's W1, here's W2. With each of these having B2 plus at least 1. And then you do this. So HF minus of S3, that's just Z adjoin U by some easy model computation. That maps to HF minus of Y by the map associated W1. There's a map here from HF plus of Y. And it turns out that this factors, and this uses the fact that B1 of W1, B2 plus of W1 was bigger than or equal to 1. And then you do the map associated to W2. HF plus of S3, which is this funny modules Z adjoin U inverse mod Z adjoin. And this composition, this is the Seiberg-Witten invariant. And then you ask, where did I use that B2 plus of W2 was at least 1? And the answer is in order to know that this composition didn't depend on which lift you chose there. So it's sort of a secondary invariant associated to the vanishing of something. The point is that this somehow comes from the fact that if I went 2 steps over, the map would be 0, or approximately would be 0. So, yeah, fine. That's not proved. So what I actually mean is it behaves exactly the same way as the Seiberg-Witten invariant in terms of basically all known properties of the Seiberg-Witten invariant, but it's not currently known to be the Seiberg-Witten invariant. I think the team who was proving these things maybe ran out of energy. One member is sitting in the back of the room, so could comment. Still writing. This stuff is incredibly hard, so it'll be proved eventually. It's just incredibly hard. Yeah, that's great. That's great. It's Egen in the back of the room for the recording and posterity. Great.
And is there some way of understanding why in the middle?
Yes, there is. No, nothing should be obvious. So there's a long exact sequence. There's a long exact sequence relating plus, minus, and the other version HF infinity, which I didn't say. But HF infinity is something that depends only on the behavior near the reducible solutions, so the ones where the spinor is 0. And of course, Egen will give a better answer. But it follows from that and from B2 plus condition that this map is 0. So that's really why this lifts. But so it's something about, well, there was some information that was happening at the reducible solutions, but that somehow that part vanished because of this homological condition. And so the right thing to do was to remember that vanishing or something. That's the best I have. Yeah, sorry, good. More questions? Okay. There was a structure part. I'm on to, whoa. Oh no, we started at 10 after. Yeah, because this is Berkeley. Of course, sorry. Construction. So, fine. Heegaard diagram. This is where the word Heegaard in Heegaard Floer comes from. Is a Riemann surface, so a closed oriented surface, sigma of some genus. And then 2G embedded, so 2G circles in sigma. So I'm going to call them alpha 1, wow, through alpha G, and beta 1 through beta G. Blue is okay in this room? Can you read the blue? Little dark? Okay. How about purple? That's worse, right? Better. Okay. That's what I know. Great. beta 1 to beta g. So the alpha circles are supposed to be pairwise disjoint. And the complement sigma minus alpha 1 to alpha g should be connected. And similarly for the beta circles. So pairwise disjoint and sigma minus beta 1 to beta g is connected. So let's draw an example. I have drawn a surface of genus 4. It will look more like a surface of genus 4 in a moment. So here are some alpha circles. So here's say alpha 1, alpha 2, alpha 3, and alpha 4. If I delete those alpha circles, you're left with a connected surface. So it can get from any point to any other by wandering around without crossing them. Don't know if that's clear. So here's some beta circles, beta 1, beta 2, beta 3, and beta 4. Okay, so there's a Heegaard diagram. Fine. This gives you a 3-manifold. Let me draw a simpler one just so that we have a slightly easier one. Here's a nice simple Heegaard. Here's a nice simple Heegaard diagram. There's a simple Heegaard diagram. Sorry, that's supposed to be beta 1. We're doing great. Beta 1. Question about the pictures? Pictures are supposed to be clear, even if what they mean is not clear. Okay, so this gives you a 3-manifold as follows. You take, so you start by thickening up sigma. So you take sigma across, I don't know, let's say the interval 1/2, 3/2. That's a bit weird. Let's say 1, 2. Sorry. Sigma across the interval 1, 2. And then you glue on thickened disks along each alpha I cross 1 and each beta I cross 2. Because I had G alpha circles and a complement was connected, you can figure out from the classification series what the complement is. A complement, sorry, what the result is. The resulting boundary component is an S2. Okay, so you glue on to this 2 B3s. I mean, each of the boundary components is S2. So this is some 3-manifold. Okay, I have presented here, if you do that, well, you can actually see doing that. You can thicken up the surface, then you can see gluing in a thickened disk inside. And you can visualize that, and you can see gluing in a thickened disk outside. So the 3-manifold you must have gotten is the only one you can see, which is S3. So this one gives you S3. Oh, actually, you can see doing the same thing here. This one also gives you S3. And if I thicken this up, a little harder to visualize, but there's a Pringles potato chip on the inside that you fill in around for each of these alpha circles, except that one is just a little disk. And you can fill in little disks for the beta. So this is also embeds in S. This embeds in S3, so it's S3. Okay. Fine. And I'll fix also a point Z in sigma not on any alpha circle or beta circle. So the invariance is going to be associated to this diagram, but it's going to be an invariant of the three manifold in the middle. Okay, so this three manifold I constructed. And okay, so for CF hat of y, you're going to consider sim g of sigma minus c, which is you take sigma cross sigma g times mod. There's an action of the symmetric group just permuting the factors. This is unordered g tuples of points, sorry, sigma minus c. So this is unordered g tuples of points in sigma, none of which are this point z. Okay. And now there are two submanifolds. You get alpha 1 cross for g and beta 1 cross beta g. And now CF hat of y is the Floer complex, so the Lagrange intersection Floer complex of T alpha and T beta. So the generators are great. Yeah, good question. So the symplectic form is a little bit tricky. If you take the symplectic area form on sigma, that gives you a symplectic form of the product, but that becomes singular when you try to along the diagonal when you try to quotient. But there's a way to smooth it out locally using some sort of patching argument, partition of unity type argument. So that was written down by Tim Peretz, and that's the symplectic form. That's a symplectic form that works here. So the symplectic form is in work of Peretz. The symplectic form only enters when you're doing Lagrange intersection Floer homology in a very minor way, in that you need it in order to know that some moduli spaces are compact. So there was an argument before that just to verify the sort of energy bounds need for compactness without knowing that there was a nice symplectic form. But yeah, there's a nice one by that sort of smoothing argument. Good. More questions? That's great.
Is it possible to recover these total right from Seiberg-Witten equations?
Great. Let me say that in just a sec. So the question is, what does this have to do with Seiberg-Witten equations? I can sketch how that's supposed to go in just a moment. So this means generators are the points in T alpha intersect T beta. So for that one, there's one. For that one, if you count, a point in T alpha intersect T beta is a G tuple of points, one on each alpha circle, one each beta circle. I mean, the intersection points, so there's one in each circle. And I think you will find 3 in that diagram. Okay. And the differential counts holomorphic maps from a disk to sim G of sigma minus C, so that part of the boundary goes to T alpha and the other half of the boundary goes to T beta. And then the plus minus I will go to the 2 points in T alpha intersect T beta. And if you want to get CF minus, you sort of work relative to Z, this point Z. So that corresponds to the divisor G cross sim G minus 1 sigma, instead of in the complement of this. So you keep track of how many times a disk intersects this divisor instead of just taking it out. What's the relationship to Seiberg-Witten theory? So here's roughly how that goes. So where did this come from? So roughly, you take, so given your manifold Y, so given your manifold Y, you can decompose as a union of two handle bodies. So H1 union along sigma to H2. So these are handle bodies. And people were considering Seiberg-Witten solutions on R cross Y. That's where you would do Seiberg-Witten Floer homology. And people said, okay, they're going to choose a metric so that there's a very long neck near sigma. So you do some neck stretching along sigma, sort of long cylindrical piece near sigma. So so long neck near sigma. So the Seiberg-Witten, this sort of schematically looks like you've got some handle body, and then, I mean, this is all sigma, right? So this is all Stoics of genus, and you got some other handle body affiliated at that end. And so there's sort of three places that you want to study the solution. One is sort of on the left part, so that's handle body cross interval minus infinity. So sorry, 0 to infinity, or handle body cross the interval minus infinity 0. And also in the middle, handle body cross, sorry, which is just a, sorry, I said that completely wrong. So let me try again and write something. So solutions, so study Seiberg-Witten equations on, the middle piece is just sigma cross, let's say R cross sigma. Right, so in the middle here, I have an R cross sigma from stretching Y, and there's another R from the R. Okay? And it turns out that this turns into some familiar equation called the vortex equations. Not the symplectic vortex equations, just the vortex equations. And the solutions correspond, the space of solutions is some symmetric product of sigma. And then the other place you're looking at is R cross handle body with this sort of cylindrical end. So you've got I can't draw it, but you've got a handle body, but where the boundary is very, very long. Okay? And this gives you this supposedly gives you a Lagrangian submanifold of this. So the solutions here that extend over the of this. So the solutions on R cross sigma that extend over this handle body is some Lagrangian submanifold. The ones that extend over the other handle body is some Lagrangian submanifolds. The intersection is the ones that extended over all of Y. And so that's sort of why the intersection shows up as something related to Seiberg-Witten. The Seiberg-Witten solutions on R cross Y, at least R invariant ones, correspond to intersection points. If you believe this story. There is work of various people making this story, parts of the story precise, but this is not how the proof goes. So the proof that Seiberg-Witten is Heegaard Floer goes by Egen and others goes by different techniques than this. But this is where the motivation came from. More questions? The theory has a, if Y is a homology sphere, the theory has a relative Z grading. The grading is a little complicated. Should I say that? I can happy to say that. Say it again.
Whether or not it has a grade.
Depends on why. How can it depend on why? That's a good question. So I can answer that. It's going to take 5 minutes. I'll do it. Okay. So grading. Yeah. So I was a graduate student. Well, I was an undergraduate and a graduate student back when Ozsváth-Szabó discovered this stuff, and so I went to a bunch of talks of theirs. And inevitably, they would try to avoid talking about the grading, and the audience would just like not accept that. So they would always, you would see, they would each talk, you would try something else to avoid having to talk about the gradings. Gradings. Let me give you the statement first, and then I endorse that move 100%. And then I'll try to explain why that has a chance of being true. So recall I said that HF hat of Y is a direct sum over spin C structures of HF hat of Y S. And HF hat of YS is what has a grading. So just for a particular given spin C structure, I'll say where that comes from, has a relative grading by Z mod the divisibility of C1 of S. So what the hell do I mean? If C1 of S is 0 or is torsion, then this is just it's just a grading by Z. Okay, so if C1 of S is torsion, this is the Z grading. But for example, if C1 of S is 14, so let's do a better example. So for example, on S2 cross S1, spin C of S2 cross S1 maps actually injects by C1 to H upper 2 of S2 cross S1, which is Z. Okay. Actually, okay. And what does it do? It hits 2Z sitting inside Z. That's what the first Chern classes of spin C structure in S2 cross S1 are. And now HF hat of S2 cross S1 in spin C structure 14 is Z mod 14 graded. G mod 14 graded. Relatively Z mod 14 graded. Okay, and now you ask me what's going on, like why is this true? So I'll connect this to what's going on in Lagrange section Floer theory. So so why? So sorry, I'm deciding how generally to talk. So we're considering, not too generally, we're considering these two Lagrangians, T alpha and T beta, inside sim G of sigma. And to, so note, they're not exact. So I mean, well, sim-g sigma isn't even. I mean, the symplectic form is not exact there anyway. So how could they be exact? So to grade CF of T alpha T beta, we'll fix. I mean, well, this isn't an exact symplectic manifold the way I've written it, so it doesn't even make sense to ask it the exact.
Okay, you say
Yeah.
when you fix it up,
It's not, well, I mean, it's closed, so closed manifolds are never exact. But
sure,
yeah, sorry.
sorry.
You could say, okay, I've deleted Z, but they're still not exact even if after you delete C. That'll show up in the what I'm about to say in the proof. So that'll follow from what I'm about to say. But so anyway, what do you think about gradings from the exact case doesn't apply because they're not. So to grade, so here's the sort of most naive way to grade a Floer complex. Fix a point, let's call it x0 in T alpha intersect T beta. Now for every other point x in T alpha intersect T beta, choose a disk, I don't know, phi, connecting x naught to x. So there's my disk, x naught and x. This, is my phi. And then I'm going to define the grading of x to be the Maslov index of phi. That is, it's the index of the d-bar operator on this disk phi. Okay, so the index of the linearized d-bar operator at phi. Okay. But there are two problems. Audience want to say what the two problems, so that's my definition of grading X. What are the two problems with this definition? Anybody who doesn't already know Heegaard Floer? I'm doing some sleight of hand here. Well, the two problems. One is that choose a disk phi, but who the hell said there was a disk phi? Maybe there is no disk relating these two intersections. Like maybe the Lagrangians look like this, and there's like a hole or something there. So there's just no, there's no disk. Okay, so two problems. One, phi might not exist. And in fact, phi exists if and only if x naught and x represent the same spin C structure. So that's each spin C structure has a relative grading. And the second one is phi might not be unique. So maybe more than one phi. If I chose a different one, maybe I had a different Maslov index. And the answer is, well, the ambiguity in mu of phi is the same as looking at the Maslov index of disks going from x naught to x naught. If I had two different disks from x naught to x, sorry, can't quite see the bottom. If I had two disks from x naught to x, they would differ by a disk going just from x naught to x naught. You take one and the other one done backwards. But this turns out to be C1 of the spin C structure evaluated on something. this disk somehow gives you an element of H2 of Y, and it's the C1 of spin-C structure by the element of H2 of Y. So there's a general story you can tell there that if you have a pair of Lagrangians inside a symplectic manifold, the Floer complex decomposes according to pi0 of the path space between them. And the ambiguity in the grading is the evaluation of the first, of whatever, the first Chern class or something on pi1 of the path space.
And how do you see that these definitions are compatible with what you got from
Well, I would say you do ask Egen, but she left. Wisely. That goes through this sort of cylindrical formulation of what's going on here, and then through Michael Hutchings' embedded contact homology. And it's a long story. But yeah, I think they checked that the gradings agree. Another way to say, yeah, there's a conceptual way, sort of. So another way to say what it's graded by is that HF hat of Y is graded by the set of homotopy classes of two-plane fields, of oriented two-plane fields on Y. So this was written down by some Berkeley graduate students about, the Heegaard Floer case about 15 years ago. Vinicius Grip and Yang Huang, I think. But so if you take the set of two-plane fields on a three-manifold has an action by Z, which is the set of two-plane fields on three-ball with given boundary. And this is also corresponds to the grading in Seiberg-Witten by thinking about something that I won't say quite, something obvious that I won't say quite right. You take the spinner and you do something. I won't get it right, sorry. But anyway, this shows up also in the Seiberg-Witten case in some obvious way that I just can't quite say. This grading is easy to see, although again, it'll take me 5 or 10 minutes to actually say, but it's easy. This is nice and geometric from the Heegaard diagram. You take the Heegaard diagram from a vector field, from a function by Morse theory, and you look at the gradient vector field at Morse function. This is like the orthogonal complement, and you do something to get rid of the zeros. So some nice geometric story here, which I'm happy to say, but it'll take a little time. More questions? We get to at least the end of part 1 then. Yeah. Oh, good. That's right. So, no, I can't say in gauge theory terms what that is. What's my problem? If you forget it, though, you get a three-manifold invariant that at least for homology spheres is independent of the three-manifold. So if you forget the extra point, you just always get Z. Sorry? Yeah, so it turns out to be important, but I can't say that quite right. But Egen or Michael could do that. That's a good question. Let me give you a couple applications just so that you have a sense of, like, for people who are not so interested in this and haven't seen it before. What is it used for? So I decided to show off a little bit with applications, both for this and bordered Floer. So I decided to take only applications proved by graduate students in the last 2 years who are currently visiting MSRI. So here's one. So 2 applications. So lots of applications have been to surgery or to concordance. I'll give you one of each. So knots K1 and K2 are concordant if K1 K1 connects some, the mirror of K2. I'll write that as MK2, bounds a disk in the 4-ball. So, and here's a knot, K1. Here's the mirror of, this is just MK1 in this case. It's just the same knot, but drawn backwards. So this is the connect sum. And I'm saying that K1 is concordant to K2 if the one connects sum, the mirror of the other bounds a disk. So this bounds a disk in B4, bounds a disk in B4. Let me say smooth. I think I'm only going to talk about smooth concordance. This bounds a smooth disk in B4. Exercise. I mean, actual exercise if you haven't seen this stuff before. So this is a statement that anything is concordant to itself. Okay, that K1 is concordant to K1. This is an equivalence relation, so that's good. Not K1 and K2 inside homology 3 spheres. So inside, I'll say what that means, but let's say homology 3 spheres, Y1 and Y2. So homology 3 spheres means Y3 with H1 of Y3 equals 0. That implies it has exactly the same homology as the 3 sphere. Okay, so it's just 3 manifolds with the same homology as the 3 sphere. Are homology concordant if, okay, there's some contractible, some W4 with boundary W4, Y1 connects the mirror of Y2. That just means the orientation reversed Y2. W should have trivial homology, and a disk D inside W with the boundary of D, K1 connects the mirror of K2. So before, these were knots K1 and K2 inside S3. So I gave you a relation on knots, concordance, and then the relation on, but now I've given you a relation on pairs of a 3 manifold and a knot, homology concordance. So what do we have? We have concordance classes form a group. Is a group, call it C, and the set of homology concordance classes, this is concordance classes in S3, set of homology concordance classes is another group, C tilde, and there's a map C that we have a homomorphism from C to C tilde, because if I have a knot in S3, it's in a homology sphere, so that's a generator. And if 2 knots co-bound a disk, well, they co-bound disk in B4, that's a perfectly good thing for my definition of C tilde. So they co-bound in a contractible manifold. Okay. This turns out to be related to studying piecewise linear topology. So understanding the relation between these 2 groups is related to understanding when you can triangulate 4 manifolds, it turns out. Or when you can, at least whatever's happening with the sort of concordance and triangulations. So theorem of Heegaard Floer from 2020. The quotient C tilde mod C contains Z to the infinity. So it's huge. So it says that there are way more knots inside other 3 manifolds, even after you mod out by this notion of concordance, than there are in S3. Next one, and then I'll stop. Brain surgery. So Dane surgery means delete a solid torus from a 3-manifold and glue it back in. Here's a conjecture from 86 of Gonzalez, Acuna, and Short. If Hugo is here, by the way, is that right? Yes, there's Hugo. Sorry, so it's his theorem. You want to wave again? Good. If Dane's surgery on K side S3 gives a manifold that decomposes a connected sum of two others. So if you get something which decomposes a connected sum of two knots, then K is a cable of another knot. Of another knot. Cable means you take your knot, and then you just have some parallel copies. You know, maybe with some twists. There's an example of a cable. It's just a bunch of parallel copies. And if you have a cable, you can see some particular ways of doing surgery to give you reducible manifolds. So this conjecture says those are the only ones. And so here's a theorem of Bodish and D'Yesso from about a month ago. The cabling conjecture is true. So for knots K, with simple Floer homology, so with thin HFK hat. Okay, I didn't quite tell you what HFK hat is. And they give a bunch of other evidence for this. Okay, this is the end of part 1 of the talk, but we've also been going for an hour. So I propose that I stop and then take questions. We didn't actually make it to bordered Floer, so you guys can choose. I'm at your disposal. It's your seminar. Okay, should we have a pause so if people are tired and they want to leave, they can leave without feeling you're in charge.
I think this is an informal seminar.
So they can just leave anyway. Okay, fine. I'll keep going then. Tried to save you all. There are no non-trivial cables that are homologically thin. Yeah, so this is that's right. So this is evidence for that. Yeah, that's right. I should know who proved that, but I've forgotten who proved that. But that follows from something about bordered Floer. Yeah, maybe it's Hedden. Yeah, the mass of Alexander is just on one line. Yeah, exactly. Okay. Bordered Floer. So everything above that wasn't attributed is due to Ozsváth and Szabó, right? So I don't know if I said everything above is Ozsváth-Szabó. And everything here that's not attributed will be joint work with Ozsváth and Thurston. Still in Thurston. Okay, so structure. Sorry. What? Let me do that first. Or why? Maybe why is the question. So the goal is formulas for how HF hat behaves when you cut y into pieces. So the Heegaard Floer homology was sort of about how does the Seiberg-Witten invariant behave if you cut your 4-manifold into pieces, but it's still very complicated. So this is about if you take your 3-manifold and cut it into simpler pieces, how does the 3-manifold invariant behave? Okay, so what we're going to do is closed, maybe connected, it's not important, surface. Let's say connected. I'll call my surface F, not to confuse it with the Heegaard surface sigma. So with connected surface F, I'm going to associate to that a differential graded algebra, A of F, over F2. So everything in the rest of the talk is going to be just with F2 coefficients. To a 3-dimensional cobordism, y from F1 to F2. So that is, I've got some surface y F1 F2. We're going to have some kind of dg or a infinity. It doesn't matter. You can just like dg bimodule CF dA of y. Okay, there were a bunch of variants, and this is one particular variant. The notation is sort of terrible, but this is the notation. This is the particular variant we're going to talk about. And now I need to tell you some properties of these. Let me first tell you a special case of this. So the algebra associated to S2 is just F2. I'll give you another couple just to get a feeling of what it looks like. So these are always finite dimensional. The definition is just combinatorial, so it's some combinatorics with diagrams. The algebra associated to Taurus looks like this: row 1, row 2, row 3, mod row 2, row 1, and row 3, row 2 are both 0. So that is, let's call this I0 and I1. Elements are paths here, except that if you see row 2, row 1 in your path, you have 0. If you see row 3, row 2, you have 0. So this is 8-dimensional. So for example, row 1, row 2 is an element of that, algebra. The algebra associated to and the differential is 0 in both of these cases. So there's no differential in either of those cases. Differential is 0. The algebra associated to a surface of genus 2 is like, I don't know, 190 dimensional. And the homology is like 92 dimensional. Maybe something, I don't know. There's some choices here, but something like 92 dimensional. But it has some simple description in terms of pictures that look like, you know, some diagrams you can draw on the plane that look like that. So some simple combinatorial Okay, these ones. The main, yeah.
Am I, in Aru's description, you would have liked the certain boundary.
Yeah, so, right, so, good question. So so there was this base point Z before, and probably my surface F also has a base point on it. And base point or boundary, you can sort of choose. You can delete a neighborhood. It's the same information. Yeah, so you can sort of think about it either way. That's a good question. Great. And the main property here is that if you compose cobordisms, well, there are two main properties. CFDA of y1, y2 is a tensor product. Tensor over A of, yes, of course. Yes.
Is it true or false that it's really Aru's description, which really actually made it into a Floer theory?
No, I think Heegaard Floer was already I mean, sorry, or you mean this stuff?
Yeah.
This stuff we didn't think of as in terms of Fukaya caddies when we were describing it. That's right. That was Aru's description that did that. I'll say what we, yeah, I'll say in a sec how we thought of this, just in case that's interesting. Yeah, it's a good question, but it wasn't defined in terms of Fukaya categories. That's right. That's right. And then in the case that if the boundary of y is just like, if y is a cobordism from S2 to itself, then CFDA of y, let's see, I'm supposed to have a bimodule over the algebra for S2 and the algebra for S2, which is just F2. So this is just a chain complex. Okay. So this is just CF hat of y, y union, with the boundaries filled in. So this really, so these two properties say that it really does compute CF hat by cutting it into pieces. You take your three manifold, you cut it into pieces. For each piece, there's a bimodule. You tensor them all together to get the CF hat for the closed thing. Trivial, no differential in either of these cases. Yeah, so just 0. So Avers genus 2, yeah, has a more interesting differential. So I have to tell you what some elements are, but like this one, it's the differentials are all ways of resolving a the elements are sort of diagonals like this, and the differentials are all ways of resolving a crossing. So I'm happy to give a precise definition of what the algebra is. It'll take, that's a sort of 15 minutes, and I wasn't going to do it if there aren't requests. More questions? Yeah.
You mentioned that you said the minus version is like more fundamental than the factor.
Yeah, that's a good question. So why haven't we done the minus version? We're working on it, but it's not done yet. So that's work in progress at present. There should be a paper any day now. Think which means a month or two. No, the algebra will be different. The algebra is worse. So we actually have a paper. We're actually only doing the minus version in the case of torus boundary at the moment. So that's already complicated enough. There's already a paper that describes what the algebra is there, but unlike here, it was finite dimensional. There, it's some infinite dimensional thing, and it has some interesting A infinity structure. So it's more complicated. It is combinatorial, but complicated. I can give that. I can give that also, but that's an hour. That's right. That's right. Yeah, yeah. Aru's description. It's easy. It's maybe easy to remember what the algebra is. I think it's pretty easy to remember from the original description, but maybe I'm a little biased. Aru's description is great. So in that language passing to CF minus, we have to fill in this puncture in the surface, and then look at some sort of Fukaya category of this closed thing relative to the divisor that we filled in. But Aru's description in terms of some sort of partially wrapped Fukaya category. So if you think about like the objects in his description, those are non-compact Lagrangians that go out to infinity. And then you fill in infinity. Those don't obviously give you compact Lagrangians at all. So there's not an apparent relationship. There's not an obvious relationship between the wrapped or partially wrapped Fukaya category, a non-compact of a projective thing minus a divisor, affine thing, with the ordinary Fukaya category of the projective thing.
Oh, really? So it's not simply like regretting the wrapping.
So so that here you sort of allow more wrapping, but then there are some other terms that come from something. And my understanding from the symplectic geometers is that story in general is not understood, like why you should do it.
My version of the theory is weird. I mean, there's some rules that from Fukaya category perspective look like somebody made up.
Yeah.
I mean,
Okay.
Okay. I'm sorry. That's maybe the Mainz version.
Mainz version. Okay, but there's this sort of passage from the Fukaya category, from wrapped Fukaya category non-compact thing to the Fukaya category of a closed thing, is I think not well understood. Andre can disagree with me. I don't know who else in this room does this stuff, but I think that's still not well understood. If you want to pass from the compact Fukaya category of a, I can say, should I write some words? So like, yeah. You have no agenda at this point. Things I can do include saying some words about the definition of the things on the board, commenting about how they relate to other mathematics, giving an application or some applications. But maybe I'll say, so what is Mina asking me about? And what did Aru do? So Aru says that the algebra A of F is equivalent in some sense to a particular partially wrapped Fukaya category of sim K of F. Let's say minus point, since my F was closed. Which is nice. It gives it's not how we came up with this A of F, but it gives another geometric interpretation of what this was. And in the other direction, it gives a computation of what this Fukaya category is. It says that, okay, if you're trying to do a computation of the Fukaya category, you can do a computation over here with this fine dimensional algebra. It's sort of nice. What is little k? Little k is like the genus of capital F. So like, sure. There's a parameter here, so I could really put a k in here, but you can capture any sim k by some variant of this. So this corresponded to, so this somehow gave us this invariant HF hat of y. Now, if I want to understand HF, so this is about HF hat of y. If I want to understand HF minus of y, this should be about the Fukaya category of sim k of F relative to, well, put that depends, relative to point cross sim k minus 1. But really, I mean, we're supposed to count curves that are now allowed to go through this base point that we took out, and so it's this.
The rules are not as if that's an ordinary point. You have to somehow, the math algorithm is very it's not an ordinary disk that they pass.
Well, it does something with it. It's, yeah, I mean, so
in fact, it knows that there's no hole there.
it knows that there's a hole there. Yeah, so what do I mean by relative? So okay. I thought to myself, I'm giving a talk to sort of a room which is half physicists. They're going to ask a bunch of questions about things I don't really know the answer to. And I was correct. So here's my attempted answer thing I don't really know the answer to. So consider I don't know, let's say a smooth algebraic variety X and a divisor D. So and Lagrangians L0 and L1 inside X, let's say disjoint from D. So our dictionary is X is sim G of sigma or sim K of F. D is Z cross sim G minus 1 of sigma. I'm still being recorded, right? This is great. And these are T alpha and T beta. Okay. So the Floer homology of L0 and L1 relative to D. So this has been studied by various people, but like one person who's made some of the main contributions, Nick Sheridan, and this is described nicely in some of his papers. His papers are very nicely written. So that's one place to look. So what do I mean? This is chain complex, or Floer, well, whatever, Floer chain complex over, I'll just call the variable the same thing. We're using Z brackets U, generated by L0 intersect L1. And with differential to be the sum over holomorphic maps U. So holomorphic disks U of the kind we were looking at before. So this is going, say, to L0, L1, X, X, Y of U to the number of times that, sorry, let's call it phi instead of U, U to the phi dot D times Y. So in the Floer differential, I keep track of how many times the disk went through the curve. So we've got a term sort of, so this is D0 plus D1 U plus, let's say, put the U up, U D1 plus U squared D2 plus dot, dot, dot. And DI counts things where it passes through the divisor. So I points 1, 2 up to I, and this is where this is like phi inverse of the divisor. And then fine. So then you can look at a whole relative Fukaya category generated by Lagrangians that are in the complement of D, and the different. I mean, you can do this to the composition operations and so on. Okay. No, that's right. So that, okay, that's right. That was Mina's question. So the degree of U is something about the first Chern class of D, is something about, something about C1 of D. But I don't think I'll get that right on the spot. If somebody knows, they can stop me. In particular, here it works out to be 2 because of the this what this particular divisor Z cross mg minus 1 is. That's right. So in Heegaard Floer 2. So the expectation is that under some conditions, yeah, okay.
If it's an ordinary point, homologic point from DC, so you have to get zero.
Yeah.
So
Yeah, I mean, it's right that like the HF hat. Yeah. Okay, I'm a little mystified by that point also. We're a little bit confused about why it works out that way also. But I mean, if you run this, but on the other hand, like the first Chern class computation for any point cross sim G minus 1 works out to give you 2 here. So
it has to be that way.
it has to be that way. But yeah.
If you think of the theory is coming from Simon's theory, say, the Simon's theory would have told you that yes, you have to pick a point
And take.
put a fermion there.
That's fair. That's fair. Okay. Yeah, I don't know. That's fair. Yeah. Fine. I'll finish the sentence just because I'm in the middle of it. So anyway, the expectation that under some conditions, come on, Robert. For this relative Fukaya category is a deformation of the is a curved A infinity deformation of the compact Fukaya category. Okay, that's almost not saying anything. That's just saying that the differential and the multiplications in this thing, in this relative one, have, it's the original one with some extra, and then some extra terms have u in front of them. Except there's some generation statement here that's not obvious. So the non-obvious thing is some generation statement here. But the relationship to there's also this, so there's also, yeah, so where's the M0 coming from? You could have disks here. You could have just discovered by adding this point that you have some disks with boundary just on a single Lagrangian, but going through infinity. So maybe you started with an affine variety, which was exact or something, and you didn't have any disks like this. Then you filled in the divisor infinity and you got some obstruction, so it became obstructed. But they all go through infinity, so they all have some u in front of them. So it's still sort of an algebraically reasonable thing as opposed to just an arbitrary curved A infinity thing. But it's not clear what the relationship with the wrapped Fukaya category. But so like wrapped Fukaya category, I think the last I asked one of these people, the sort of wrapped Fukaya category of what's my notation? X minus D versus relative Fukaya category. I think the relationship is not known. Because there's not a map on objects. If I give you a Lagrange that goes out to D in some way, it's not clear how you would close that up to get a, like there's no map. Here there was sort of a map. You had a Lagrangian in X minus D, that's also Lagrangian X. But if you have a Lagrangian in X minus D that's not compact, it's not a Lagrangian in X. So it's not clear what the statement should be, as I understand it. Again, it's not my stuff. But Mohammed is an expert on this stuff. I mean, Mohammed does this stuff.
So was discovered on right?
No.
Well, okay.
It was discovered by sort of thinking. Maybe. I think I don't know. I don't know. I mean, that's not how we try to give that translation when we can. We don't, but this point is serious. Like we don't know. how to, I mean, so it's some of this point for what we're thinking about now. But yeah, for the previous case, maybe, though none of the proofs go that way. So, but maybe. That's true. That's true. Yeah, so let me mention that. So that's true. So though again, none of the proofs don't go that way either. So the proofs somehow indirect. Yeah, so I mean, I don't know what it's inspired by, but it's certainly consistent with that. So Handsome and yeah. Sorry, I'm getting lazy. Handsome, Rasmussen, Watson showed that the category of modules over this algebra associated to the torus. So this, it's there, that thing on the far right, corresponds to the set of immersed curves in T2 with local systems. T2 minus a point. Thanks, Ian. No. That's right. So they take some. Yeah, I mean, I think that's true for a physicist. Like, I think that's true at the physics level of rigor, but I think it's very far from proved at the mathematics level. There's I mean, and probably it's not true in general. Like it's probably true for, maybe it's true for the examples that people care about, but it's probably not. I mean, I think it's one of these statements that's like probably not true in general because of sort of generation problems again. But it's certainly not. It's, yeah, I mean, so anyway, there's work of Kontsevich and others on this sort of story in general, but it's not. I don't think I'm being recorded still. I don't think you can actually, nobody has, some people say this follows from that, but nobody's actually written down a proof that this follows from that, and I don't see it. So somebody should write down that proof. But that would be great. Somebody should do that, Maxime, on the recording. Great. What a good leading question. Yeah, that's where it came from. So what we were doing, yeah, let's do that for the last couple of minutes. So let me say one, I was going to give you applications I won't do because of time, but remark, this gives a way of computing HF hat, see code linked from my web page. And there's some tutorials there also. So if you're actually doing computations, because maybe you have some other invariant that you think is Heegaard Floer and you want to, see what it does in some examples, you can use this to act, you get, for relatively simple manifolds, you plug it into the computer and it'll tell you what the answer is. So it's not just like, in principle, it should compute, but there's computer code and tutorials. Okay, yeah, so where from? That's Ian's question. So take a Heegaard diagram. Here's a Heegaard diagram. I only draw diagrams for S3 today. So here's a diagram for S3. Cut it along a circle, some appropriate circle. So I'm going to just cut it in half. Okay, cut it in half. Blue. Now, holomorphic curves in sim G of sigma. So holomorphic, let's say disks. What is a map from a disk to sim G of sigma? So it's just a multi-valued map to sigma, because for each point of the disk, I've got G points in sigma. So this is just a multi-valued map to sigma. But when you took beginning complex analysis, you thought about multi-valued maps like square root a different way. They had Riemann surfaces associated to them. So these correspond to the other way of thinking about multi-valued maps, which is diagrams of some surface that branch covers the disk and maps to sigma, where this is a G-fold branch cover. That was the other way you thought about G-fold multi-valued maps. So this corresponds to maps. Instead of the disk, I'm just going to write that as a strip. So to write it as 0, 1 cross. Let me write it the way I usually do. Sigma, take the sigma factor. And then the disk, I'm just going to write as 0, 1 cross R. Right, a map to here and a map to there is the same as a map to the product. And this is basically the disk. OK. And now for this sort of diagram, if I look at sigma cross 0, 1 cross R, here's 0, 1. Sorry. So here was sigma. Here's 0, 1. Here's R. Okay, so here's sigma cross 0, 1 cross R. And if I think about a holomorphic curve there, I'm going to have, well, I didn't remind you of the boundary conditions. My disk was going to T alpha over here and T beta over there. So my boundary conditions look like, sorry, purple is better. My boundary conditions look like I have some cylinder there. That's my beta along that side. I have some cylinders along this side. But these are not compact. Okay. And what my curves are going to do, they're going to have some behavior at minus infinity in R. That's going to be my generator X, right? X was down there at minus infinity. You have some behavior at plus infinity R. That's going to be my generator Y. They're going to wander along on this boundary. They're going to wander along the beta circle. And on this one, they go along the alphas. But at some points, they might go out to the boundary of sigma. So here they can go out to boundary sigma. So when it goes out to boundary sigma, you see some chords like this. Like here's maybe row 1 and row 2, row 3 along the boundary. So the way that the module works is I would say, OK, we have our holomorphic disk that starts at X, goes out to boundary sigma at some chord, say row 1, row 2, row 3. Or sorry, row, let me not call it row, row prime, row double prime. And so I'm going to interpret that as either the differential of X is like row, row prime, row double prime times Y, or as a higher product, M4 of X, row, row prime, row double prime. And so there's sort of two variants. And then thinking about what happens in the codimension 1 boundary of this space is what leads to the definition of the algebra, the module. So that's where it came from. And that's still the perspective that we have been working from and do computations from. But by some magic, this turns out to correspond to this thing about Fukaya categories that Arud talks about. And OK, it's not so, I mean, in hindsight, it's not so much magic. At that time, it's sort of magic. But once you see it, it's not so bad. Should I stop there? More? They give an application. What would you like? Sorry, how you define it?
Yeah. Also here questions like intersection after the circles. You have to have like the same number of components.
Yeah. So I
you have the pure blue circle purely on the right.
Yeah. So. Well, sorry.
Arud's calculation of the algebra was really a calculation.
Yeah, it was really a calculation.
It's completely rigorous. Were you actually able to calculate?
Yeah. Well, define what is calculate. I mean, if you give me an arbitrary Heegaard diagram and you say write down all the holomorphic curves, I can't do that.
But here you could.
For this particular diagram, I can.
And for all the diagrams that arise, for homogeneous,
we were able to. We can do it for generators for the mapping class group, or sort of. We can do it for enough basic pieces that you can glue the basic pieces together to get anything. Yeah, so we can do it for some specific basic pieces, and then it turns out to be enough. But no, not for a general thing. But I mean, nobody can do that. No, there will not be trouble if a branch point moves the boundary. But that will contribute to why the algebra is defined the way it was. So the algebra sort of understands what happens in codimension 1 at the boundary. So that's how it's defined. Let me do something useful. Let me do an example, and we'll see some degeneration happen in that example, and that'll explain part of the algebra. Instead of a definition. Good. Yeah, this idea was introduced in some sense by me in the cylindrical formulation. Though the idea of like that a multi-valued function can be viewed in 2 ways is probably older than that.
So there are 2 approaches. The original one and illustrated.
Yeah.
Is there any reason that you chose this cylindrical one?
There is a reason that we chose the cylindrical one here. I can answer that. The point is, it's not, you can't see it in genus 1 boundary, but for genus 2 boundary, we can. So let's have a genus 2. Let's have a genus 2 Heegaard. Let's have a genus 2 handle body on the board. I'm going to be lazy about drawing handles. So this is a handle. It goes from A to A. It's OK. Here's a handle from B to B. I should have put in the title, this will not be interesting to people who know something about ordered Floer homology in the abstract. Oh well, next time. So I've just drawn 2 arcs. This is one arc, and there's another arc. And I'll do that again. And now I'm deciding, sorry, let's do Fine. Okay. So here's this is a particular genus 2 handle body. So I've got two beta circles. I can label them. Here's beta 1, and here's beta 2, and I've got a whole bunch of alpha arcs. So these are halves of alpha circles. If I like, you could imagine sitting over here is some other diagram, and you glued the two together, you get an ordinary Heegaard diagram. It's like I've taken a half of a ordinary Heegaard diagram. I have 4 alpha arcs. Did I say 2? Yeah, 4 alpha arcs. Thank you. So let's call this point A, X, Y, Z. So CFD is going to be generated generated sort of over the algebra by AX, AY, and AZ. This is going to look a little bit stupid, but that's fine. I could probably have chosen a better example. Here is, let's give these names. So let's call this like row 1, row 2, row 3. And I'm going to call, so that row 1 is just this arc on the boundary. Row 2 is that one, and row 3 is that one. Okay. And this arc, I'm going to give the name row 2, 3. Okay, it's like row 2 followed by row 3. So here's row 4, row 5, row 6, and row 7. The base point, if you want, is there. Here's a disk that goes from, okay, labeling wasn't great. This goes from Z to X with the conventions I put on the board before. So boundary of Z, this disk contributes a term X. Here's a different disk. So this disk goes out, it goes through row 3, and then it comes back to Y. Okay. So this region here is a perfectly good discant thing. So Z plus row 3 Y. Here's another disk from Z going out to row 2 and then back to X. So sorry, from Y going out to row 2 and back to X. So this is giving me boundary Y is equal to row 2 X. Sim, so let me punt that question. No, we're in Sim 2, but there's another component, just a constant at A that you're not seeing. So there's another component that's sort of constant here and you're not seeing. Sorry, I should have, but sorry, this shouldn't be Z. This should be, sorry, this is AZ, AY, AX, AY, AX. I mean, I just dropped the A's. Here's another disk that contributes. You can go out, orientation, right? Go out that way, down to here, along. Let's see, that is here, and then back there and that. So it's these two regions glued together as a disk. So this gives me boundary of AZ is equal to row 5, row 6 times AZ. And boundary of AY is row 5, row 6 times AY, etc. I've now written down all of the index 1 holomorphic disks here. I mean, you would need to check that by computing some indices or something.
How do you know this triangular is beta stack plot? That I'm not going to draw something so complicated that
You mean if you draw some complicated diagram here?
No, not complicated. Some complicated shows the beta stack. I'm going to
Yeah.
find them around.
Yeah. I mean, you can always make the alpha standard. No, again,
I can't draw it. I can't compute from an arbitrary diagram. I can compute for enough diagrams that I can build up any three manifold from those pieces. But there's no way I can compute the holomorphic curves in an arbitrary diagram. No, but so a generator is going to have, when I complete it to a closed diagram, I'm going to want to have a point on each beta circle and a point on each alpha, and a point on each alpha circle. So I need to use each beta circle, and I can't use any alpha circle more than once. Those are the rules. So these are the only ways of choosing points. So I got one in each beta circle. I don't use any alpha, sorry, arc more than once.
Is it also clear that there's no way for this to not become
like to go out here? Or oh, yeah. The point is that if it isn't constant, no. So there are two kinds. There are two ways it could be not constant. One is I could take this disk times that disk. That won't have index 1. So I could take the disk I drew here times one of the non-trivial ones here, but then you can slide them relative to each other, and that's index 2. The other thing is you could possibly go over, you could have something that goes, that's longer here. That's prevented because it would have to go over this region, and then that's got Z in it, and I didn't tell you, but I'm not allowing this to go over Z. So that's just the multiplicity at Z is required to be 0. But that's special to the diagram. I mean, normally, you'd be much more complicated disks. I've drawn the simplest diagram I could possibly draw. The left and right sides are not equal, but the relation you want to check is, sorry, haha, plus row 5, row 6, AZ. I means contain, equal means contains as a term. So this is really a plus. Row 5, row 6, AY. I apologize. Okay, good. Thank you. Sorry. And so now you ask, is d squared equal to 0? And if we think about whether d squared is 0, we'll get some relations. So for this to be true, we need some relations like row 5, row 6 times row 3 is equal to row 3 times row 5, row 6. Just write down what d squared is. And another one we'll need is that row 3, row 2 is equal to 0. Again, that's going from AZ to AY to AX, and this is the only term. Then each of these relations corresponds to something that happens in codimension 1 in the moduli spaces. And so what we did is we wrote down what are all the things that happen in codimension 1 in these sorts of moduli spaces. And then that turned out to give a nice algebra, and that's the algebra that we wrote down. And then the modules satisfy these relations.
You could have computed. I mean, you have to do it by
I mean, what's a first principle? I mean, we wrote down, we didn't compute it from the Fukaya category. But yeah, I mean, if you knew Aru's work, then he could.
I mean, it's Fukaya category.
I don't know any first principles. I mean,
in the end, right, what you're saying, there's some algebra of
yeah.
morphism between those terms, right?
Yes.
So you should be able to get it by counting some frequency.
Oh, I agree. And I didn't answer the question that was asked, which was, why do we use a cylindrical setting? And the answer is, if you think about this as a Fukaya category, where you sort of filled in the boundary here, these Lagrangians are not smooth. And this divisor, this thing we filled in is not smooth. It's some sort of singular thing. So, but in particular, the Lagrangians these alphas don't extend smoothly. If I just collapse the boundary to point take symmetric product, you end up with something that's not smooth.
But this is precisely where his stuff happens, right?
That's right. That's right. He did something. He's a little bit clever, but still, if you try to do sort of Fukaya kind of a closed of like sim G sigma, not deleting this divisor, you end up with some Lagrangians that are not smooth in this story, and we didn't like that. we didn't know what to do with those. So that's why we worked in the cylindrical setting where things were okay. Fine. I should stop because we're at 4:05, and people presumably need to do other things. Thank you all.
Thank you so much.
I should say I'm happy to stay around forever and answer questions, but
I just want to find, you said that this theory is just Z2 graded, yeah.
I said it's over Z2. The grading is complicated. So the grading on the algebra. So sorry. So the coefficients we did are F2. The grading A of F is graded by a non-commutative group, which is a Z central extension of H1 of F. So it's graded by some group G, which is a central extension of H1 of F. And this group corresponds to, again, two plane fields, homotopy class of two plane fields on 0, 1 cross F. So on a thickened up version of F. So there's a multiplication just by concatenation in 0, 1. And I don't know, and that gives you a group. And that group happens to be a central extension of H1 of F. So the grading is a little complicated, and the modules are graded by G sets, and it's sort of it's a little bit of a mess. But that's, again, there's some general Fukaya category story where that grading, that's how gradings work if you do something with anchored Lagrangians in a sufficiently general setting.
Can I ask you a question?
Of course.
So here you have 4 alpha cycles and 2 beta cycles.
Yeah.
It doesn't matter.
So that you can always have it so that if you have the number of 1/2 the number of alpha arcs plus the number of alpha circles is going to be equal to the number of beta circles. And that's somehow something about how this cutting if you think about Euler characteristics or something, it's how the cutting should work. Yeah, that's a good question.
Right. Let's thank the speaker again.
Thank you very much for your patience.